Hey guys, Mrs. Thompson here, and today we're going to talk about evaporation, vapor pressure, and boiling, and what's the difference between them. First of all, we need to talk about vaporization. And vaporization is just that phase change from a liquid to a gas. So it's right here. In order to change liquid to gas, we do have to add energy, and it will vaporize. There are two types of vaporization. One is evaporation, the other is boiling. We're going to go through each one of those. Okay, we'll start with evaporation. Now, evaporation is just vaporization at the surface of a liquid. It's what this says here. It says it's the process of a liquid becoming a gas without boiling. So, a couple things have to happen in order for those particles to be able to evaporate. One is those have to be at the surface of the liquid. And two, they have to have enough kinetic energy to break the intermolecular forces that are holding them in the liquid state. Okay, on the left, here you have a beaker filled with water. When we measure temperature, what we're actually measuring is the average kinetic energy of that part of the particles within the entire liquid. We call that an average because you have some particles that are different temperatures. And so let's say color-wise, if I put some particles in there that are cold, some that are a little warmer, and then some that are pretty hot. Those particles, if we were to graph them on a graph, would look something like this. Okay, this is a Maxwell-Boltzmann distribution graph, and what it shows is the number of particles and how much energy they have. So the amount of kinetic energy they have, it increases from here to here. So on our graph, the cold particles would be in this region, the warmer particles somewhere here, and then our nice hot particles would be closer to the end because they have a lot of kinetic energy. Now, let's say if we were to draw a line for the minimum amount of energy that it takes for those particles to vaporize, let's say that's right here. That means that all the particles within this part of the graph, right here, those particles would have enough energy to escape the liquid form, and they turn into a vapor. So we'd write particles here would have enough energy to break their intermolecular forces. And so you end up with particles evaporating. Remember, that only happens at the surface for evaporation. Evaporation has an overall cooling effect, and the reason it has an overall cooling effect is because it's the warm particles that leave. And as those warm particles leave, they take their energy with them, and so it makes the water below or liquid below cooler. Just like when you perspire. As you perspire, your body needs to give off energy in order to get that sweat molecule or water to leave the surface of your skin. And so you provide the energy to make that water evaporate, and then you feel cooler. All right. Another thing, if temperature increases, the rate at which it evaporates increases. So you notice this is another Maxwell-Boltzmann distribution. At higher temperatures, the particles that have more energy are greater. And so there is a greater chance that the particles at the surface are going to have enough energy in order to evaporate. All right, next one. Vapor pressure. And so vapor pressure is just the pressure that's exerted by the vapor. And so it's exerted on the top of the liquid. And it actually has a role in holding the liquid in a solution, because those molecules bounce around in the container. They bounce over the top of the liquid and hold these inside. Okay, you can see differences in vapor pressure in one of two ways. So vapor pressure is increased as temperature increases. So as you give those particles more energy to escape, they have enough energy to escape and are above the liquid. So the vapor pressure above the liquid is higher. Or if you're comparing two different substances, the vapor pressure of the liquid that has the weakest intermolecular forces will be greater. The reason for that is because those intermolecular forces are not holding them in the solution as much. And so they're free to escape and create pressure over the top of the liquid. Okay, we can use a graph of vapor pressure versus temperature to compare intermolecular forces for different liquids. so this graph, you have vapor pressure on the left, so it's from top to bottom it increases. And then you have temperature on the bottom, so from left to right it increases in temperature. We're going to pick a specific temperature to look at compare the three different liquids, ethanol, water, and diethyl ether. So I'm picking 20 degrees. So if I draw a line from 20 degrees, I'm going to check to see which one has the highest vapor pressure. Okay, well, you can see the one at the top here has something like 470 torr in terms of vapor pressure. So it has the highest vapor pressure. We'd say diethyl ether has the highest vapor pressure. Okay, what does that mean about its intermolecular forces? Remember that as the intermolecular forces get weaker, the particles are able to escape, creating more vapor pressure. So diethyl ether would have the weakest intermolecular force. Okay, now let's look at the bottom. The first line that it crossed was water. And so water would have the lowest vapor pressure. It's somewhere around maybe 10 torr. Okay, so it has the lowest vapor pressure. What that means is it's holding the liquid particles into the liquid form instead of letting them escape. And so there's less vapor over the top of the liquid. And so that means that its intermolecular forces are the strongest. Okay. So the higher the vapor pressure, the weaker the intermolecular force. The lower the vapor pressure, the stronger the intermolecular force. Okay. Let's discuss boiling. Now, all boiling is vaporization that happens under the surface. So it's the formation of a vapor onto the surface. In order to boil, what has to happen is the vapor pressure, the gas particles pushing down above the liquid, has to equal the atmospheric pressure. So that's the rest of the pressure pushing down. So once this happens, the vapor pressure can overcome the atmospheric pressure, and you'll see bubbles start to form in the bottom of the liquid. Those bubbles are not air bubbles. They're the gaseous form of whatever liquid is inside. And those then rise, and you start to see boiling. The boiling point happens at a certain temperature for a particular pressure. Now, if pressure changes, the boiling point temperature changes. So it says here, boiling point is the temperature at which a liquid boils. Things that have strong intermolecular forces will have high boiling points because you have to add lots of energy to get them to overcome those strong intermolecular forces. Another term that you need to know is normal. Normal just means at standard condition, which is at sea level. So at sea level, the pressure is 1 atmosphere, because there's 1 atmosphere above us, or 760 torr, 760 millimeters of mercury, 101.3 kilopascals. Remember, all those units are equal. Okay. At this pressure, we find the normal boiling point, so the temperature at which a substance boils. For water, the normal boiling point is 100 degrees Celsius. Hopefully you know that. Okay. So you can actually see that from a graph of vapor pressure versus temperature. And so when each substance reaches atmospheric pressure, because that's when things boil, when the atmospheric pressure equals the vapor pressure, we can read the boiling point temperature. So for diethyl ether at 760 torr, it's 34.5. Just reading it down here, the numbers are there. 34.5 degrees Celsius. For water, 100 degrees Celsius. All right, so you also need to know that boiling point actually changes as elevation changes. This just means that as you go up in elevation, what you have is less of an atmosphere, the pressure is lower. And remember that things boil when the atmospheric pressure equals the vapor pressure. Well, if the atmospheric pressure is low, then it's going to reach that point at much lower temperatures. And so what you get when you're trying to boil water for tea up on top of a mountain is you get water boiling at like 97 degrees Celsius. Or if you're going way higher, let's see, you've got all the way up to Mount Logan in Canada, their water boils at 80 degrees Celsius. If you wanted to know how the temperature at which water boils on Mount Everest, it's 69.94 degrees Celsius. That's so high up there. All right. Here's a cool little trick that deals with not elevation, but changing the atmospheric pressure in order to make a liquid boil at room temperature. So we're going to watch this.
And now, amount of water and a thermometer. So let's begin the experiment. I'm going to place our beaker of water into the bell jar.
Bell jar is just used to vacuum out the atmospheric pressure above the liquid.
Close this valve to isolate the chamber so the air can't get in. And I'm going to open this one to let the air out. As the pressure is dropping, the boiling point of the water is dropping. And as that boiling point goes past room temperature, it will start to boil. Even though the water is boiling, it's actually not hot. In fact, it's colder than when it started. The reason that the temperature is dropping is because when the liquid molecules boil off, they take some energy from the liquid. This is called the latent heat of vaporization, and it causes the energy of the water to drop, which means the temperature drops. So as the water has boiled off and transferred its energy away from the water, you can see that the temperature has dropped to around 0 on the thermometer, and ice crystals have formed in the water. Okay, that's our experiment. I've shown you that water changes phase in a vacuum. If you're going to replicate this experiment, please have an adult thermometer. Let's begin the experiment. I'm going to place
Pretty cool. It changed into a solid by boiling.
Close up the bell jar again. And now close this valve to isolate the chamber so the air can't
here's this chart here just to go over the difference between evaporation and boiling. In evaporation, this happens at all temperatures. It's constantly happening even if the liquid is cold. It occurs for boiling at one specific temperature, and that's the boiling point temperature. Where is this happening? Well, for evaporation, it's happening only at the surface. For boiling, once it reaches that temperature, it's happening throughout the entire liquid.
They take some energy
is this process spontaneous, meaning does it just happen? Well, evaporation is spontaneous. It's constantly happening because you have some particles that are warmer than others. And in boiling, it only happens when the vapor pressure is equal to the atmospheric pressure.
Dropped to around 0 on the thermometer.
Alright, in terms of intermolecular forces, we need to remember this. They're the weak forces. We will have more liquid turning into gas, so it's not as strong. It's going to vaporize more. For the strong forces, you're going to get less gas. And so for weak forces, they have high vapor pressures. Strong intermolecular forces have low vapor pressures. Weak intermolecular forces have a high evaporation rate, so they evaporate quickly, whereas strong forces have a low one. Weak forces tend to have a low boiling point because you don't have to heat them as much to get them to separate, whereas strong intermolecular forces will have high boiling points. All right, so let's actually do some. We're going to just decide, is this a strong or a weak attractive force? So if something has a high vapor pressure, okay, that means lots of the particles are above the liquid because they are able to evaporate, which means we have a weak intermolecular force. If it has a high boiling point, that means that it has lots of attractions holding those molecules in the liquid form. So you have to add lots of energy. So you have strong intermolecular forces. Low boiling point, well, that's the opposite. Doesn't take much energy, so it's weak. All right, you try the next 3. All right, let's see how you did. Low vapor pressure would have strong intermolecular forces because it's holding them in, and none of them are floating on top, or very little, excuse me. Evaporates rapidly. That's weak because they're going everywhere. They're able to leave. Evaporates slowly. Well, that's strong. Okay, well, I hope that made sense. I will see you in class, and hopefully you bring me some questions.